Hello guys, how are you doing?
Good afternoon, Professor.
Good.
Good. You?
Good.
Good. Was first snow today in the morning. I mean, not first, but kind of first significant enough to see on the ground.
You're in Astana, right?
Yes. Okay. Let's wait a bit. Maybe more people will join. Okay. I see today is Friday and not so many people are excited about oscillations, but we have already 7 participants. Let's proceed further since we need to finish today this topic, oscillations, and there are a number of questions which should be discussed after our detailed derivation of the simple harmonic motion equation for a system spring block without considering any friction. So we did last time very detailed step-by-step derivation of this equation, considered this like its derivatives first and second in order to get the velocity as a function of time and acceleration. Also discussed the kinetic potential and total mechanical energy of simple harmonic motion, and showed how we, at the end of the discussion, we showed how it's possible to determine the velocity at any given position without like excluding time as a variable from the equation. And that is possible by using the concept of total mechanical energy being constant for simple harmonic motion without friction and equal to the maximum potential energy of the stretched or compressed spring at the beginning of the motion. Okay, with the system spring block, we pretty much did everything what is possible in terms of understanding its motion. Let us proceed further, and the next one very common system which exhibits periodic motion is how it's called, it's a pendulum. Yeah, and today we are going to start our discussion from deriving equation for pendulum oscillations and proceed further for other cases. Okay, now I change the screen and let us consider a standard pendulum. So we have some body which is quite small in comparison to the length of this rope at which it is hanged, and it has certain mass m. Here is this dashed line is the position of equilibrium. So here we have an angle theta. When we pull this body from the equilibrium condition, from equilibrium condition is theta equal 0. Then what do we get as a result? Obviously, we have here some weight of the body, mg. Then we have some tension in the rope, this thread, T. And we can consider two components of our weight. It will be one component going here and one component going here. So this is angle theta also. And that's why a component which goes, let's call it radial component, just goes along the radius of the motion, because it's actually moving along part of the circle trajectory. And this component will be mg cosine theta. And this tangential component, which will always trying to move the body to the condition to equilibrium condition when theta is equal to 0, will be mg sinus theta. So this direction of the tangential component of weight, as I mentioned, it always tends to move the body to the position theta equal 0. And that's why its direction will be always opposite to the displacement of the body. So we can write that minus, okay, this F tangential, which is equal mg sinus theta, is equal, according to the second law of motion, the product of mass and tangential acceleration. So since we know that it's always directed in opposite way to the, an opposite direction to the displacement, because it always wants to return the body in the equilibrium condition at theta equal 0, we can write minus mg sinus theta is equal to mass times this tangential acceleration. It will be d square s d t square. So this s is the path or displacement what this body performs. That's why we can describe the tangential acceleration via this second derivative of the path along this part of circular trajectory, which the body does. So from the definition of the angle in like radians, which we measure in radians, we have a part, some segment of the circle. Here is our angle theta. Here is radius. And this is S, is the length of the segment of the circle. So the angle theta in radians is equal to the ratio between the length of this segment S divided by radius. So we were talking about this definition of radians, of angles previously, but just to remind you what is definition of radian. And in this case, instead of radius, we will operate with L, with the length of this rope, actual length of the pendulum. That's why we can write that S, the path which the body performs, is equal to the product of L and angle theta in radians. So now we can substitute expression for S as product of L and theta here in this second derivative, and we will get the following. Will be minus mg sinus theta equal to ml, because this L, the length of the pendulum, doesn't change. Here will be d square theta dt square. So we can cancel out the mass from the left and right side, and write the following equation from here. It will be a differential equation. Maybe in order to make it a bit better, more convenient, we will divide it by L. So left and right side, and then put everything in one side. So it will be d square theta divided by dt square plus g divided by L sinus theta equal to 0. Okay, so let us write this equation, this differential equation, on the next slide, and we can continue. So it will be d square theta dt square plus gl sinus theta equal to 0. It is known from the geometry that at small theta, small angle theta, which is less than 0.2 radians, which corresponds to something about 10 degrees. It is with high accuracy, the following assumption is valid, that sinus theta is almost equal to theta itself. So that's why, assuming that we don't have theta, like amplitude theta value larger than 0.2 radians, we can simplify this differential equation, assuming this condition. So instead of sinus theta, we will end up only with theta. So let us do it. So it will be d squared theta divided by dt squared plus gl divided by L, and here will be theta equal to 0. Now, next to this equation, I will write equation which we derived during last discussion when we considered system which is the combination of a spring with a block. So there we had an equation which gives us differential equations which operates with the position x and with a function as x of t. So that was d square x dt square plus k divided by m times x equal to 0. So as you see, they have very similar, they are actually the same type of equation, is second order linear differential equation, where equivalent for x for position in the case of the spring with a block. We have theta, which is the angle of deflection of our pendulum from equilibrium condition. Since these since these two equations are of the same type, the solution, obviously, we will not go through step-by-step solution because it actually is the same procedure as that one which we already did during last discussion, but the solution will be in the same form, and that's why theta. So we are interested how theta depends on time. So this solution of the differential equation, in analogy to what we have done previously with this equation for the spring and block, will be equal to theta maximum times cosinus omega t plus phi, where maximum theta is the amplitude value of the angle, and omega stands here for the square root of g divided by L. So we had before for the spring and block k divided by m, and here for pendulum we have j divided by L. So from this equation we already can make an important conclusion that the angular frequency for the oscillations of pendulum doesn't depend on the mass of the body. So we don't have mass here, we have only acceleration of free fall, g, numerator, and L, length of the pendulum, in the denominator. That is kind of important finding from this derivation. And can you remind, please, under which conditions this is valid?
When angle is less than 10 degrees, it's
Yes.
frictionless. I mean, spring.
Yeah, sure. That's right. We frictionless until now, we don't consider any friction. That will be our next step in understanding. So up to now, we consider only frictionless. It's correct. And also very important factor that angle is less than 10 degrees or 0.2 radians, because if we don't make this simplification, like this step, the equations will be not identical, the solution will be different. So if the angle is small, that's the reason why we can use the same format for the solution of this differential equation. And as a result, we get angular frequency independent on mass and defined only by J divided by L. So this you should keep in mind, and because many equations which are derived for applications in different systems, they all have certain suggestions at the beginning or limits for application. And that's very important to understand this, that you cannot apply the same equation for even the same system which operates or functions in under different conditions. So there should be always some limits for application. So in this case, this angle should be not big. Okay, so since we can also, based on this expression for the angular frequency, we can write expression for the period, which is important. Quite often it's used period for the oscillation of a pendulum. It will be 2 pi divided by omega, and this is 2 pi square root of L divided by G. And frequency also, it will be 1 over T, 1 over 2 pi square root of G divided by L. So what is interesting with such a system, it's very like this. It's so-called simple pendulum. When we have a point body attached to a long thread, like rope. For such a system, we can easily calculate the acceleration of free fall. So if you take a look at this equation for the period, let's take T squared equal to 4 pi square L divided by G. And from here, we can express G as 4 pi square L divided by T squared. So length of the pendulum, we can easily measure. 4 pi square is a constant, and period of the oscillation, we can also easily measure with quite high accuracy, specifically if we count, like measure time, not just for one period, but let's say for 100 periods, and then divide it by number of periods. So we can, with quite high accuracy, determine the period of oscillations. And that is the way, very easy way, simple to calculate the acceleration of free fall. Okay, so we are done now with the simple pendulum. Let's go and discuss physical pendulum. That is a bit more complicated system, but from other side, it's kind of a bit closer adjusted to our everyday life experience. So when we operate not with point bodies, mathematical points, but some distributed, some bodies with certain shape and distributed mass. So let us assume that we have such body, just some random distribution. Here we have some point O at which this body is fixed and can rotate about this point. So if the, for instance, axis goes perpendicular to the plane of the image, so it can rotate in the plane of the image about axis which goes perpendicularly to the image through point O. And we also know for this system the position of the center of mass. So this is our center of mass. Let's put this horizontal line, which defines the line which goes through the axis of rotation. And there is a distance d between the point where the axis of rotation goes through and the center of mass of this body. So here, like this distance between the horizontal vertical line and the center of mass will be d times sinus theta, and theta is this angle. Okay, so obviously, since it's center of mass, we can apply here like the vector of the weight of this body. It's mg. And now we want to calculate what will be the torque which this weight of the body exerts on the body, on this body with respect to the axis which goes through point O. So as you remember, we need to take this distance perpendicular which goes on the line, vertical line in this case, which goes through the center of point O, and multiply it by force, which is perpendicular to this distance. So this torque will be equal to mg times, so this is the force, the weight, and then we have to multiply it by this distance, and this is d times sinus theta. Okay, so we have the torque. So if there are no other forces, we assume that we have isolated system and there are no other forces acting on this body, the total torque with respect to the axis which goes through point O will be equal, maybe not here, yeah, let's write like this, total torque, and this is total torque, will be also equal to the product of, do you remember how torque is related to the moment of inertia? So we have similar dependence for just force and acceleration. Our
Omega.
not omega, but because omega is angular.
Alpha. I mean angular acceleration.
Exactly. Yeah, you're right. So for second law of motion, like total force, we would write that it's product of mass and linear acceleration. So in analog to second law of motion, the total torque is equal to the moment of inertia, capital I, times alpha, which is our angular acceleration. Good. So once we have these two equations, and we also need to take into account that this torque always tries to push the system back to equilibrium condition when center of mass will stay on this vertical line which goes through the point O. We need to write that minus mg times d sinus theta is equal to I times alpha. So this minus because it always opposite to the this force, no, not force, this torque tries to put the system back in the equilibrium condition when theta is equal to 0. So if we increase theta, this torque tries to decrease it. That's why we put this minus here, and this is equal to the product of moment of inertia and angular acceleration. And we can write the expression of angular acceleration as in the form of the second derivative from the angle theta. So it will be I times d square theta divided by dt squared. Okay, now let us divide left and right side by moment of inertia. I, and put everything in one side. It will be d square theta divided by dt square plus mg d divided by I, moment of inertia, times sinus theta equal to 0. Okay, so now we need to again apply this simplification, assuming that sinus theta are approximately equal to theta at theta less than 0.2 radians. And also we can consider that this prefactor is equal to omega square. So from here we can write that omega is equal to, maybe we can do it later, maybe it will be confusing. So now we just substitute the sinus theta with theta, d square theta dt square plus mgd divided by I times theta equal 0. So again, it has the same form as two previous differential equations. That's why, based on the same form of differential equation, it will have the same form of solution. So our solution for this physical pendulum, which is not just some idealistic mathematical model, I mean, we can make a simple pendulum quite close to this requirements for the ideal system, but obviously we'll always have some deviation because we don't have mathematical point as a body. But if the length of the pendulum is very long, that could be a very good approximation. But this is the case for any randomly shaped body. The solution for this period, its oscillation, will be given in the same form as for the simple pendulum, but with just a little bit of a difference. It will be theta equal to theta max time cosinus of omega t plus phi, where omega is equal to square root of mg d divided by I. So this is kind of interesting behavior. This randomly shaped body will follow the same equation of dependence theta on time. However, the frequency, angular frequency, will be defined by the mass of the body, and it will be important like weight of the body, because it's in denominator we have product mg, and also it will be defined by the moment of inertia for this body with respect the axis which goes perpendicular to point O, goes through this point O perpendicular to the plane of the image, and proportional to the distance between the point O and the center of mass for this body. So if, for instance, we know the location of the center of mass and also location of the point O, we know the distance, so we can measure the angular frequency or period and determine unknown moment of inertia for this body with respect to the axis which goes through point O perpendicular to the plane of the image, which in other way could be quite challenging to calculate, taking into account the shape, complex shape of the body. So that is analogy to the simple pendulum, which with certain corrections and adjustments can be applied to any physical pendulum. That's kind of useful for certain applications. So for this case, we also need to write the expression for the period because it's quite important parameter. It will be 2 pi divided by omega, 2 pi square root of moment of inertia divided by mgd. Okay, so now I guess we are done with the most important and common oscillators. So we had initially simple harmonic motion derived by on the example of spring block system. Then we had simple pendulum, and now we got equations for the physical pendulum. At this point, we need to go to next step and consider the case with some so-called damping oscillations. So far, as we already mentioned several times, we only considered frictionless case, no dissipation of mechanical energy, no conservative forces, non-conservative forces which cause some transformation of mechanical energy to internal energy. However, in real life, there obviously always we have some friction or some drag, some resistance of air, which should be taken into account. So for this purpose, let us consider some system which moves not very fast, and that's why this drag force for resistance in air or in some liquid would be proportional to the velocity. So this will be drag force is equal to, let's say, minus b v. And this minus because it's always in opposite direction to velocity, and b is some coefficient for the drag force. And it's proportional to the linearly proportional to the velocity. In this case, the total force which is applied on some oscillator will be equal. Let's consider an example of a spring and a block. So the total force which is applied to the block will be spring force minus kx. Then will be this drag force, like resistance of environment for this moment, will be minus bv, and this is equal to ma, according to the second law of motion. So now we can take into account the relationship between va and derivatives of x and rewrite this equation. It will be minus kx minus b, so v is first derivative of x over t, will be times dx dt equal to md square x dt square. Now let us divide this by m to get rid of this coefficient next to second derivative, and this will be d square x over dt square plus b divided by m dx dt and plus k divided by m x equal to 0. So this is also second order linear differential equation. However, it's different from the previous forms because we got some coefficient next to first derivative, and our characteristic, we didn't have this term in previous equation. It was just d square x over dt square plus k divided by m times x. So now we get another additional force, which is drag force, and we got one more term in this differential equation. So the procedure to solve this, we will not go step by step, but procedure to solve, since it's also square, like second order linear differential equation, we write the characteristic equation. So lambda in second power plus b m lambda, because here we have just first derivative, and plus a m equal to 0. And then we solve this characteristic equation for lambda 1 and 2, and based on what we get the instructions according to rules of solving this type of differential equations, in which form the solution will be for this particular case. So in this case, the solution for x as a function of t will be equal to a. And also we apply boundary conditions, so it will kind of the same procedure as we did for the at the beginning for simple harmonic motion, but obviously our solution for lambda will be different. That's why the form of the final equation, which describes this function x t, will be a bit different. So in particular, it will be for this case, a amplitude times e in the power of minus b divided by 2m t times cosinus omega t plus phi. So we had just a times cosinus, but now since we have this additional drag force, the solution was changed by adding another term, which is e exponent in the power of minus b divided by m times t. And in the case of not also for omega, it will not be the same as for the system without, for the spring block system without drag force. So as you remember, it was square root square root of k divided by m for frictionless case. For the case with friction, will be equal to square root of k divided by m minus b divided by 2m squared. Okay, you see that this frequency will be smaller because without drag force, for instance, if b coefficient next to velocity is equal to 0, then it would be just square root of k divided by m. But since it's not equal to 0, angular frequency will be smaller than it would be if there is no drag force. But from other side, we see that this frequency also doesn't depend on time, which is important. So it means if we have drag force, the frequency will not reduce. So the oscillation will continue with the same frequency, but the amplitude will exponentially decay over time, because we have not just constant a, but a times e in the power of minus b divided by 2m times t. And if we show the oscillation over time, t, and here is amplitude value of our oscillation. So here is plus, here is minus a at the beginning would be, but over time, instead of going with the same amplitude, this oscillation will have the same period, the same angular frequency, but amplitude will exponentially decrease. And this is described by this dependence, a times e minus b divided by 2m times t. So it's exponentially decays over time. Another thing which maybe should be mentioned, that this frequency, which is square root of k divided by m, can be denoted as omega 0 and called natural frequency of the system. So means natural frequencies would be frequency at which it oscillates, this system spring block would oscillate if there is no drag force. And that's why we can write that the frequency with the drag force will be equal to omega 0 square minus b divided by 2m squared. So this natural frequency is also sometimes called resonance frequency. If the external force will be applied with the same frequency as natural frequency of the system, then would be observed such called resonance. We don't have time to consider the case of oscillations with applying external periodic force, so-called forced oscillations. But you can read it in the textbook. Definitely pay attention on this. That is specific case when frequency of the external force coincides with the natural or so-called resonance frequency of the system. Amplitude of the oscillation can go up, up, up until it doesn't reach some extreme values and could even destroy the system if it cannot withstand the so huge amplitudes of oscillations. That's interesting effect, which can also be observed in electrical circuits, not only in mechanical systems. And for sure you will consider these effects in the second course, Physics 2, when you study RC, resistor, capacitor chains in response to some external AC signal, alternating current signal, which is applied to this electrical circuits. So that's why these oscillations have quite broad application, which are not limited only to mechanical systems. However, in the course of mechanics, we deal with mechanical systems and give this detailed description, explanation of the concept and derivation of basic equations on the example of simple mechanical systems. Okay, guys. Thank you very much for your attention. Have a good evening. And don't forget to focus on the textbook, because that is the key source of information for you. We just provide this discussion to help you understand the material and concepts of physics. But now the textbook is the important source. So please take your time and work with the textbook also.
Thank you, Professor. Goodbye.
You're welcome. Have a good evening. Bye-bye. Take care.